Hi everyone, we meet again in the final part of network layer, part 7, which is routing in network layer. So we have already learned up to Internet Control Management Protocol. In this last lesson, in the network layer, we're going to learn more about routing protocols in the Internet. So recall that the first component in the network layer is the IP protocol, which we have learned on the addressing, datagram format, and packet handling conventions. Next, we have already learned about the ICMP protocol, and currently we are in this part, which is the routing protocol. Remember that internet is a combination of networks connected by routers. So when a datagram, for example, wants to go from source to destination, it will probably pass through many routers until it reaches the router attached to the destination network. So routing principle basically deals with how to deliver a datagram. A datagram can be delivered whether to a destination on the local network. So in this case, it can be sent directly, and it can use ARP to obtain corresponding hardware address. And the datagram can also be sent to other destinations that is not on the same network as the source. So this will be sent via routers. Okay, so let's see an example here. Host A here is directly connected to B, C, D, E, F, G. So in case A wants to send a datagram to a host in network N1, it will do so via routers R1. And similarly, if A wants to send data to a host in the network N2 here, it will do so via R2, routers R2. So typically, a host is attached directly to one router, okay, which is the default router for the host. So whenever a host sends a packet, the packet is transferred via its default router. Okay, so we refer to the default router of the source host as the source router, and the default router of the destination host as the destination router. For example, if in this case, the router the destination router for the destination in N2 is R2. So basically, the purpose of a routing algorithm is simple. Okay, given a set of routers with the link connected to the routers, a routing algorithm will find a good path from source router to the destination router. Okay, so as I've said before, a routing algorithm finds a good path from source to destination. So this routing algorithm is actually part of network layer responsible for deciding which output line an incoming packet should be transmitted to, because there can be many links from a router to go to any destination. Okay, so the decision to route or the decision to find the route is based on optimization. Which of the available pathways is the optimum pathway? So the definition of the optimum here can depends on the routing protocol itself, whether it wants to find the shortest path or the fastest path, because sometimes the shortest path is not the same as the fastest path. Okay, so the challenges of the routing algorithm is to avoid loops. Okay, so to avoid loops within the network, because we don't want the datagram to circling around the network in many loops. And also the challenges is to react to failures. For example, if one of the routers fail to perform, so how is the routing algorithm going to find an alternative path to the destination? Also react to topology changes. For example, there is a new router that joins the network, which can send a packet to the destination, or maybe some of the routers are also not available or congested at the routers. So this routing algorithm task is to find the path to the destination, okay, using based on these topology changes. And another challenges is discover topology. Okay, for example, like I said before, a new nodes join the network, okay, or perhaps a new network is set up, and routing algorithm needs to discover the topology, means the location of all the nodes in the network for routing. And also routing table and routing algorithm can be classified into static or also dynamic. Okay, so a static table means the one with the manual entries. Okay, manual entry, perhaps the intervention from the people. And a dynamic table, on the other hand, is the one that can update it automatically when there is a change somewhere in the internet. Okay, so in other words, it can adapt to any changes in the internet. So there are many other ways to classify routing algorithm. For example, we can also classify into centralized versus decentralized algorithm. Now, forwarding a datagram means to place the packet in its route to its destination. Okay, it means that a datagram needs to get to the next hop from the routing table. So it also gets a hardware address for the next hop based on ARP protocol, okay, the one that we have learned before, to get the physical address for the next hop, or ARP cache, okay, means from the memory. So when a router wants to forward a datagram, it has to reduce the time to leave field in the packet. Remember that IP address in the IP header, it has TTL or time to leave field. So these numbers in the time to leave has to be reduced by 1, normally by 1. Okay, once a router wants to forward a datagram packet, it also needs to recompute header checksum. Okay. So the router will send the datagram on local network to the next hop's hardware address, and the address fields in the IP header should not be modified, exception for the source routing option fields. Okay, so again, forwarding here means to deliver packet to the next hop, okay, which can be the final destination or the intermediate connecting device. Okay, for the router task is to receive datagrams on all physical networks. So it looks up in a routing table to forward datagrams to their next hops or forward datagrams to their destination. So routing algorithm is the one who is responsible to create this routing table for the router to use it to find the next hop address or the destination address. So a router should know about all locally available routers. All locally available routers here means that all the routers connected in the same network as this router. Okay, so router talks to other routers using this routing protocol, and a router can also be the address itself. It means that the router can also be the destination for that datagram. For the host, the task is to receive datagrams. It can also send out datagrams according to routing table. Okay, so this routing table is the one that is created by the routing algorithm. Okay, so the host can just send the datagram to the destination if the destination is in the same local network as the host, or it can send to the datagram to the next hop router if it is non-local. It means that it has to go through another routers, okay, not the router that it is connected to, to send this datagram. Okay, however, host can also leave without knowing other routers. It means that it can just know its router. Okay, so this router needs to be active to send all the datagrams by this host. Okay, a host can also multi-home. It means that it can have multiple network address. Okay, however, this is kind of dangerous. For example, when forwarding packets, it has to be careful to avoid the routing loops. Okay, the next we're going to learn about the intra and also inter-domain routing. So we know the internet can be so large and so massive that one routing protocol cannot handle the task of updating the routing tables of all routers. Okay, because it is so large. Okay, so we can imagine how many users are using the internet nowadays. So for this reason, an internet here is divided into autonomous system or AS here. So autonomous system is actually a group of networks and routers under the authority of a single administration. So it can be known as, it can be divided into intra-domain routing and also inter-domain routing. Okay, so for intra-domain routing protocol, it is used to determine routing performed within the autonomous system. Okay. However, for the inter-domain routing, it is used to routing between the different autonomous system. So autonomous system chooses one or more intra-domain routing protocols to handle routing inside the autonomous system. However, only one inter-domain routing protocol that handles routing between autonomous systems. So, okay, so let us look at the example of the autonomous system here. Each autonomous system here consists of a group of routers that are typically under the same administrative control. Okay, for example, here in this autonomous system, there are two routers here. So these routers within the same autonomous system normally run the same routing algorithm, and it has information about each other. Okay, so the routing algorithm running within this autonomous system is called intra-autonomous system routing protocol. Okay, and it is necessary, of course, to connect this autonomous system to another autonomous system, and thus one or more routers here in an autonomous system will have the added task of forwarding packets to the destination outside of the autonomous system. Okay, so R1 here is connected to R3, which is in another autonomous system, and R3 here is connected to R2 in another autonomous system. So these routers are called gateway routers. So you can imagine for the real internet, it will be more of this autonomous system. So obtaining this information from the neighboring autonomous system, for example, R1 here wants to get the information from R3 and R2. These tasks are handled by inter-autonomous system routing protocol. Okay, inter-autonomous system routing protocol. Right. So since this inter-autonomous system routing protocol involve communication between the autonomous system, okay, these three must run the same inter-domain routing protocol, inter-domain autonomous system routing protocol. Okay, so routing protocols basically can also, as I've said before, can be divided into intra-domain and inter-domain, okay, for the internet. Okay, so it is used to discover routes to the destination, or to the next routers, or to the next network. Okay, it is also used to propagate route information. For example, if topology changes, okay, and also for the validation of the routes. Okay, some of the routes perhaps is not available, okay, because of the congestion, or perhaps is not available because of the failure of the intermediate routers, and so on. So the routing protocol also used to check route consistency, okay, whether the information is correct or not correct in the routing algorithm. Okay, so there are several types of intra-domain routing protocols. For example, distance vector. Okay, and so an example of distance vector protocol is RIP, or routing information protocol. Okay, another type of intra-domain routing protocol is link state. Okay, so an example is OSPF, or open shortest path first. Okay, so the example of the algorithm in OSPF is Ch4 algorithm. For the interdomain, okay, it uses path vector. Okay, an example of path vector is border gateway protocol. Okay, so border gateway protocol is used for the interdomain routing protocol of the autonomous system. Okay, so moving on to the next slide. Okay, I have said before that routing algorithm can also be categorized into non-adaptive, which is static, and also dynamic, which is also adaptive. Okay, so for static routing algorithms, routes change very slow over time because of the human intervention. For example, human manually editing routers forwarding table. Unlike dynamic algorithm, it changes the routing path according to the network. Okay, perhaps according to the network traffic loads, or for maybe because of the topology change. So topology change can be cause of nodes or routers failure, or perhaps a new routers or hosts are added to the network. So the dynamic algorithm can be run either periodically in direct response to topology or link cost changes. Okay, so it is more responsive to the network based compared to the static algorithm. So example of static algorithms here is shortest path routing, which is simple and easy to understand because this shortest path routing task is to choose a route between a given pair of routers. So algorithm will find the shortest path between them on the graph. Okay, it can be based on the number of hops, and it can also be based on the physical distance. Another one is flooding. Okay, flooding can be, for example, broadcast the packets in which all its neighbors receive that source packet. Okay. For the flooding, when a node receives a broadcast packet, it will duplicate the packet and forwards to all of its neighbors, okay, except the neighbor from which it received the packet. Okay. For the distance vector routing, it can be seen in the autonomous system with it can be seen as an autonomous system with all routers and network as a graph. Okay, so a set of nodes and lines is called edges connecting the nodes. So this is the distance vector routing. So example of the distance vector routing is Bellman-Ford. Okay, this Bellman-Ford is an algorithm that that is based on the graph theory, where a router is represented by a node and a network is represented by a link connected to these two nodes. Okay, so an example of this is the routing information protocol. Right. So the next one is the link state routing. Okay, it has different philosophy as the distance vector routing. Okay, for this link state routing, each node has the entire topology of the domain. Okay, it has the list of nodes, it has the list of links, and how they are connected. Okay, so this for the link state routing, it can use Ch4 algorithm to build its routing table. So example here is the open shortest path first, or OSPF protocol. Okay, so the next one we are going to learn about Ch4 algorithm. So basically, Ch4's algorithm, it solves the problem to find the shortest path from a point in a graph to a destination. Okay, so it can be used for the network. Okay, to find the shortest path from one point to one point in the network. Okay, so one can find the shortest path from a given source to all points in the graph in the same time. So in this example of the network, we can imagine that a source here is a source host, and all points in the graph can be the next hop of this source. So this problem is sometimes called the single source shortest path problem. Okay, so I will play this video for you to listen to the Ch4 algorithm routing table on how to find the path, the shortest path from A here to basically the G.
For the last of our graph demonstrations, we're going to take a look at Dijkstra's algorithm, and we're going to apply Dijkstra's algorithm to a directed weighted graph. First step, we're going to start out at A, and we're going to figure out where we can get to from A that's better than what we've already got. Now again, all of these are infinite to start out with, so anything is going to be an improvement over that. So we take a look at all of the edges originating at A. We have an edge from A to B at cost 20. Well, 20 is better than infinity, so we have a new lowest cost path from A to B, and that's cost 20, and that's from vertex A. We have another one from A to G, that's cost 90, that's also from A, and we have another one from A to D, and that's 80, and that also originates in vertex A. And all of the remainder are going to be infinity, because we have no paths to any of those vertices yet. In the next step, we're going to take a look at the lowest cost path of all the ones we have so far. We have 80, 90, a lot of infinities, but we have a 20. 20 is the best we've done so far. So we're going to pick that as our lowest cost path, and we're going to say that that one is now complete. So in our next round, we're going to start out the search at the place where that lowest cost path has taken us, which is B. Now B, we already know. The lowest cost path is 20. But we're going to see where else we can get to from B that we haven't been to before. Well, B only has one edge originating, and that takes us to vertex F. Now we haven't been to F before, so its cost is currently infinity. So the cost to get to F via B is just 10 more than whatever the cost was to get to B. So in other words, 20 plus 10 is 30. And that's a path via B. Everything else is unchanged, so we're just going to copy it down. In the next round, we're going to take a look at all of the paths we have so far, excluding the one that we've already picked. And we're going to find the lowest cost path. Well, in this case, it's the newest one that we've added, which is 30 to F. So F is going to be our starting point for the next round. Now we have two edges originating from F, one which takes us from F to C at a cost of 10. Now that's 10 plus the cost we have already of getting to F, 30. So 30 plus 10 is 40. To get to C, 40 is better than infinity. So we have a path to C, cost of 40, and it comes from F. We also have an edge from F to D. Now the cost of that edge is 40. Now 40 plus the cost of A to B to F is a total of 30 plus 40 is 70. Now our path currently to D is cost 80. 70 is an improvement, so we'll take 70 instead. And that's via F. And nothing else changes. So 20 from A, still no way to get to E, 30 from B, 90 from A, and still no path to H either. In the next round, we're going to pick the lowest cost path of all of the ones we haven't completed yet, and that's this one over here. So our path to vertex C at cost of 40. So C is going to be our starting point for the next round. Now there's several edges originating at C. One takes us back to F at cost 50. Now that would give us a total cost of, well, 40 to C plus 50 more is a total of 90. Now 90 is not better than 30, which is of course what we'd expect because we've already found the lowest cost F. But we do have one from C to H, and that's in addition to the cost of getting to C in the first place, which was 40. So 40 plus 20 is 60. 60 is a big improvement over infinity, so we'll take that one. Path to H, cost of 60, coming from C. We also have an edge from C to D at a cost of 10. Now 10 plus the cost to get to C of 40 is a total of 50, which gives us a path from A to B to F to C to D of cost 50, which is less than the cost of the path we have so far. So we have another improvement. 50 to get to D via C instead. And that's the only change. So everything else gets copied down. And that's still the best path to B, and that's still the best path to C, and that's still the best path to F. But of what we've got left, this path to D is now the lowest cost path. So we finally settled on a path to D that's going to be the best that we can get. So that's at a cost of 50. So now let's take a look at where we can get to from vertex D. Vertex D, we can get to vertex G at a cost of, well, 50 to get to D in the first place, plus 20 from D to G. Grand total of 70. 70 to get to G, well, that's an improvement over the direct route from A to G, which was 90. So 70 is better than 90. So we pick 70 instead, and that's via D. But that's the only new path we have. That's the only edge we have originating in D. So everything else just gets copied down once again. this one, and this one, and this one, this one. So now our next lowest cost path is this one to H at a cost of 16. So we're going to pick that for the next round, and we're going to start exploring paths, starting from vertex H. Now vertex H is very interesting because there's no edges originating there, so there's nothing more we can do. All we're going to do is say that everything stays the same as it was before by copying everything down. And all the finished paths are still finished. And of the remaining unfinished paths, the lowest cost one is this one over here at cost 70. So we're going to mark that one as finished, and we're going to add that vertex G, and we're going to take a look at all the edges starting from G. There's only one edge originating at G. That takes us back to A at a cost of 20, grand total of 90 to do a round trip back to A, but we weren't trying to do a round trip in the first place, so that adds no new information. Everything just gets copied down. All of these are complete, which leaves us with one last value, which is E, as value of infinity. Now in this case, value of infinity tells us that there's no path to E at all. And in fact, if we take a look at the vertex E, we can see, of course, that there are no edges leading into E, which means that there's not going to be any way of getting there. And having the value infinity left over as our result shows us that there is, in fact, no path to E. So we can mark it is done. That's the best path we can get, none at all. And now our Dijkstra's algorithm, finding the lowest cost paths from A to all the other vertices in our graph, is complete.
Basically, from the video just now, you can know the shortest path from A to all the points here in the network. Okay, so please have a look on another example that I also put in the e-learning. Okay, so please scan here for your attendance, and please take all the lesson that you have listened to in the network layer. Okay, this is for my record. Thank you very much. So we meet again in the next lesson, which is chapter 5. Thank you very much.